Thank you very much. Good morning, all of you. Now we are in the Unit 3 in Water Resources Engineering 2. Earth dams and spillways is the topic, and we were discussing several classes regarding the earth dams, also about the spillways also, like what is a spillway, types of spillways, design of Vogel spillway profile, and then what are the various energy dissipators and stilling basin, jump height curve, and tailwater rating curve. So today's class, we will be concentrating on stilling basins, two types, like Indian type stilling basin and USPR stilling basin, followed by spillway gates. What is this stilling basin? It is a structure in which energy dissipation action is confined. This will be provided at the downstream portion of the spillway, may be extended for certain length. The phenomenon of hydraulic jump is basically used for dissipating the energy. It may be called hydraulic jump type stilling basin. We may use certain auxiliary devices also, so as to contain the whole process of energy dissipation, confining to the total length of the stilling basin. We may use auxiliary devices like tube blocks, baffles, and seals. So these will act as the additional measure for controlling the jumps. Types of stilling basins. Two varieties, like USPR stilling basins and Indian stilling basins, are pure of Indian standard stilling basins. Various types of stilling basins have been generalized for use in different types of works by various agencies. The design of these basins have been developed on the basis of long experience, also by conducting several model studies, keeping in view the protection obtained, consistent, of course, with economy also. These basins are not simple concrete aprons, but they are generally provided with certain auxiliary devices like tube blocks, baffles, and end seals. In the previous class, we have seen what are the tube blocks, what are the end seals, and what are the baffles which are provided on the apron at the downstream part of the spillway. The USBR has standardized the stilling basins for different ranges of Froude numbers. Similarly, Bureau of Indian Standard has also standardized certain stilling basins for use under different conditions. Stilling basins 1 and 2 with a horizontal apron and 3 and 4 with the sloping apron have been standardized. Let us see both USPR and BIS stilling basins. Let us start with the USBR basins. USBR has standardized the stilling basin for different range of the Froude number. So depending on the initial Froude number FR1 or F1, these have been finalized. USBR stilling basin 2 is recommended for use on large structures such as dam spillways, large canal structures, when the Froude number is greater than 4.5. The stilling basin also we can see, and the length of the basin depends upon the Froude number, which is given here in the table. For the Froude number 4, the length of the basin will be about 3.6 times the sequent depth in the hydraulic jump Y2. Similarly, Froude number 6, it is 4 times Y2. For Froude number 8, 4.2 times Y2. And if the Froude number is greater than 10, 4.3 times Y2 would be the total length of the stilling basin. So this is the USPR stilling basin, may be extending for a length of 3.6 times the sequent depth to 4.3 times the sequent depth, depending on the initial Froude number. So in this also you can see the total length of the stilling basin, 4.3 times Y2. 4.3 times Y2, the stilling basin. USBR stilling basin 2. This figure also gives you how the length is finalized for the stilling basin. USP or stilling basin 4 is used for the Froude number lying between 2.5 to 4.5. This basin is applicable only on to rectangular cross sections. Large chute blocks are used to control the oscillating waves. The floor of the basin may be set as to provide 5 to 10% more depth than Y2. And the length of the basin is kept equal to about 5 times Y2 minus Y1. Y2, the sequent depth of the hydraulic jump. Y1 is the initial depth. 5 times Y2 minus Y1 would be the length of the stilling basin type 4. So you can see here 5 times Y, the difference of Y2 and Y1. Y2 minus Y1. Here it is shown Y1 minus Y2. It is Y2 minus Y1 gives you the total length of the stilling basin LB. Stilling basin LB. Coming to BAS stilling basins, the BAS laid down the criteria for the design of hydraulic jump type stilling basins for rectangular cross sections. Chute blocks, baffles, and sills are also provided in the basin. And different types, if you see, type 1 and type 2. When the tailwater rating curve approximately follows the jump height curve, the hydraulic jump stilling basin with a horizontal apron provides the best solution for dissipating the energy. There are two types of stilling basins with a horizontal apron. Stilling basin in which the Froude number FR1 less than 4.5 generally encountered for weirs and barrages. The stilling basin in which the Froude number greater than 4.5 generally occurs in dams. Stilling basin type 1, the basin floor, the basin length and floor level, length and basin appurtenances are designed like elevation of the floor. Let HL be the head loss in the hydraulic jump. Q is the discharge per unit width. And then you have the values of YC, Y1, Y2, like YC, Y1 and Y2, maybe the initial sequence depths, and YC is the critical depth. Then total head loss in the hydraulic jump type of stilling basin will be Y2 minus Y1 whole cube by 4 Y1 Y2, where Y1 and Y2 are the conjugate depths, initial depth and sequent depth. Also, having known the value of Y1, Y2 can be computed. The very standard formula while analyzing the hydraulic jump, we have used the same formula. Y2 will be equal to Y1 by 2 plus square root of Y1 square by 4 plus 2Q square by G by 1. And the critical depth of YC will be equal to Q square by G whole to the power 1 by 3, or else cube root of Q square by G. The elevation of the floor is given by upstream total energy minus the upstream specific energy. Total energy is the sum of Y plus V square by 2G plus Z, whereas the specific energy will be Y plus V square by 2G. So the elevation of the floor will be the difference between the total energy and specific energy. Basin length, depth of the stilling basin type 1. Generally, the floor should not be raised above the level required from Y2 consideration, because Y2 is the sequent depth, and if it reaches the value of Y2 at the downstream portion, then only hydraulic jump will form. So if it becomes necessary to raise the floor due to site conditions, the same should not exceed 15% of Y2. The basin for this case should be provided with the chute blocks and baffles. The dimensions of the chute blocks, baffles, and sills are given in the figure. What should be the size is given here. And the elevation of, for the type 2, the elevation of the basin floor is fixed, as in the case of type 1, for type 2 also. The length of the basin is determined from the figure, and the basin floor is fixed, as in the case of type 1, and the dimensions of the appendices also are given in the figure. Then type 3, this type of stilling basin is adopted where tailwater curve is higher than the Y2 curve at all discharges. It is not possible to standardize the design criteria for sloping aprons in the case of horizontal apron. The slope and overall shape of the apron are determined from economic considerations. The length is judged by the type and soundness of the riverbed downstream. The design criteria serves only as a guide in proportioning the sloping apron designs. Much depends upon the individual judgments also. the basin should be supplemented by an end sill of the height equal to 0.052, 0.2 times the sequential depth of Y2 with an upstream slope of 2:1 to 3:1 will be provided. This is the upstream slope which is provided here. Stilling basin type 4, it is suitable for the case where the tailwater depth at the maximum discharge exceeds Y2 considerably but is equal to or slightly greater than Y2 at lower discharges. Like in type 2, it is not possible to standardize the design criteria. The design criteria laid down by BIS serves only as a guide in arriving at the apparent dimensions, which depend mainly upon the practical considerations. So we have seen about two basic categories of the stilling basins: USBR stilling basin and Bureau of Indian Standard stilling basin. And in all these cases, no hydraulic jump analysis is used to fix the length of the floor. Similarly, the elevation of the floor will be fixed based on the specific energy, the difference of the total energy and specific energy. And the length of the floor will be taken to be 5 times Y2 minus Y1 in case of Bureau of Indian Standards. Okay, slight differences from one type to the other type depending on the criteria that where you are using, the case where you are using, you need to select the specific type of the stilling basin. In most of the cases, it is going by the practical considerations to fix the dimensions. What should be the height, what should be the size, and where to provide the end sill, location, size of the end sill. All these are based on the practical considerations. Okay. Now we see about the spillway crest gates. We know at the crest of the spillway, if the gate is provided, the full reservoir level can be increased. So we have two types of spillways: gated spillway, ungated spillway. If a ungated spillway is provided, the crest level itself will be the FRL. Over and above that, whatever is the water that is coming into the reservoir flows to the downstream portion straight. So the crest level will be equal to the FRL, full reservoir, in case of ungated spillway. If a gate is provided, then the full reservoir level can be over and above the crest level. So you can be able to store more water by providing the gates. So you can see here in this figure, several gates are provided. The purpose of these gates is to increase the full reservoir level on the upstream side, which will enable to have more capacity of the reservoir. By installing the gates over the spillways, additional storage can be made available, especially during low water flows. During the period of low water, the water which is joining into the reservoir try to be stored by providing these gates, by closing the gates. During the flood times, these gates are raised so that the full use of the spillway capacity can be made and the water can be safely discharged to the downstream portion. So we discuss about some types of the spillway crest gates. So look at this figure. You have a clear picture of the gates which are provided. So these are the gates which are provided over and above the crest level of the spillway. So this is the crest level of the spillway. By providing these gates, the water level on the upstream side can be increased. For example, if there is low flow period into the reservoir, the gates will be closed. The water which is coming into the reservoir can be stored without letting off to the downstream portion. On the other side, during the flood period, the gates can be opened. That means the position of the gate will not be here. It will be somewhere here. The gate will be opened. Thereby, the water can be safely disposed over the surface of the spillway to flow to the downstream portion. So this will happen during the flood period. So a small video here to understand about the spillway gates. Please go through this.
Crest gate is fitted to the top of a river weir or dam to provide additional storage as well as minimizing upstream flooding. It is totally automatic, not requiring any electromechanical intervention. The crest gate is closed, with the buoyancy tank empty to float on the water and increase the water level in the dam. As the water level rises due to a flood, water decants into an inlet weir which feeds the water through hollow ducted radial arms into the buoyancy tank. The tank slowly fills, and as the weight of water in the buoyancy tank exceeds the flotation on the tank, the crest gate rotates downwards to open. The spillway then freely discharges the flood waters over the spillway, taking with it large objects carried down by the flood waters. As the flood abates and the water level subsides, water flowing into the inlet weir reduces and then stops flowing into the flotation tank. The water in the tank is constantly discharging through discharge pipes downstream of the spillway. This slowly decants water out of the tank to reduce the ballast weight in the tank, and the crest gate floats up to its fully closed position. The crest gate therefore opens automatically to pass flood waters and closes automatically to retain the full supply level. By setting the inlet weirs at different water levels, the crest gates can open in sequence in response to the rising water levels and thereby effectively pass the incoming flood. The combination of crest gates and scour gates on river weirs makes an effective and flexible structure to minimize sedimentation and flotsam behind river weirs. The crest gate.
Yeah, so we have seen in this video how automatically the gates are getting opened and closed using the buoyancy principle. So based on this, if the floodwater is increasing, the crest gate moves down to enable more water to flow to the downstream portion. On the other hand, as the water level is receding in the reservoir, the crest gate moves up because of the simple buoyancy principle. The crest gate moves up, allowing the water to store on the upstream side. So entire thing is automated. In this case, the operation of the crest gate is fully automated. Now we see about the types of crest gates. Dropping shutters or permanent flash boards. So this is one type of crest gate. Dropping shutter. They are something like wooden panels which are provided here so that they will obstruct the flow and the water will be stored on the upstream side. They consist of wooden panel, usually 1 to 1.25 meters high. They are hinged at the bottom and supported against the water pressure by the struts. So these are the dropping shutters. The shutters fall flat on the crest when the supporting struts are tripped. So these shutters can be raised or lowered from an overhead cable way. Various types of automatic shutters which drop and raise because automatically have been used in use nowadays. Sometimes flash boards may be used as temporary gates on the spillways of minor importance. These fresh boards are supported by pins on the edges. The flash boards are supported by the pins on the edges. They may be braced or hinged, and automatic flash boards are designed in such a way that they fall automatically at certain head. So the flash boards, like wooden shutters, are provided here. You can see here, these are the flash boards. They will be held up at this position. As and when required, they will be dropped so that they directly fall in through the groove and the water level and upstream side can rise. The second category of the gates is the stop logs. Stop logs consist of wooden beams or planks placed one upon the other and spanning in the grooves between the spillway piers. They can be placed and removed either by hand or with hoisting mechanism. They are useful for the minor works. So this is the groove. So within this groove, a stop log can be provided. The stop log can be provided. Number of stop logs may be kept one over the other to increase the height. So this is how the stop logs. You can see number of stop logs are provided here. You have a concrete block here, something like a pier. So in between these two piers, a groove is there. So in this groove, these top blocks one over the other are placed. So they can be dropped one after the other. So whatever is the maximum water level required up to which those number of logs can be dropped. Third one is the vertical lift gates. These gates span horizontally between the grooves made in the piers. The grooves are lined with steel channel sections to provide a smooth bearing surface and are known as the groove guides. The gates move between the groove guides. The gates are usually made of steel. Because of the hydrostatic pressure, large functional frictional forces are developed in these guides. So the vertical lift gates may be like this, the third category, what we are looking at in this picture. The vertical lift gates are provided in the groove. So these are the gates. These are the gates. Radial gates is the fourth category. A radial gate has a curved water supporting face made of steel. The curved water face, which is in the shape of a sector of a circle, is properly braced by steel framework, which is pivoted on a horizontal shaft called pin. The pins are anchored in the downstream portion of the spillway pier. The gate rotates above the fixed horizontal axis. Counterweights are used to reduce the lifting force. Radial gates can be used with a smaller lifting force for all heads than the vertical lift gates. The gate can be lifted by means of ropes and chains, acting simultaneously at both ends or with the help of power-driven winches. So you have a radial gate here. You can see this is the radial gate, which is moving over the crest. So this is the spillway crest. You may observe in the figure, this is the spillway. The crest of the spillway is provided with this radial gate. So this radial gate is operated with respect to a pivot here. So with respect to this pivot, the radial gate can be operated up and down. The dotted line here shows that the gate is moved up. When the gate is moved up, the water is flowing directly over the crest of the spillway. Directly over the crest of the spillway. You can notice here that the total height, which can be increased, which can be raised for the water level by providing this gate, is 10 meters in one of the problem. So this is the crest level of the spillway. Over and above the crest level of the spillway, the water may be stored even to a level of about 10 meters here. About 10 meters here. So this is how the radial gates will be provided. Over the crest of the spillway, the radial gate is provided. Fifth one is the drum gate. Drum gates are useful for longer spans of the order of 40 meters or so and medium heights, say maybe about 10 meters. The drum gate consists of a segment of a cylinder which may be raised above the crest or may be lowered into the recess made into the top of the spillway. The drum gate require large recess and hence are not suitable for the smaller spillways. So this is a drum gate. So instead of directly moving over the crest, you may observe here a floating drum is moving towards the axis of the spillway crest, towards the axis of the spillway. Yes. So you have a hollow gate section that floats on the water in the case of a drum gate. So this is how a drum gate would be provided. So to conclude, USPR has standardized the stilling basins for different ranges of Froude numbers. Stilling basin type 2 is adopted in the situations where Froude number is greater than 4.5. Type 4 is adopted for the Froude number less than 4.5. In both types, we use the chute blocks, baffles, and endicils, which are used to reduce the length of the stilling basin. ISA has classified the stilling basins into 4 different types, ISA or BISC, 1, 2, 3, and 4. Type 1 and Type 2 are used with horizontal apron. Type 3 and Type 4 are used with sloping aprons. Spillway crest gates are divided, other parts. Crest gates are divided into various types, like dropping shutters, top logs, vertical lift, and radial and drum gates are there. The last 3 are used for large structures. So we have seen basically about the spillway crest gates and the stilling basins which are proposed by USPR as well as Bureau of Indian Standards. A small experimentation has been carried out by one of the researchers